3 by 1 plus 1. So the fourth degree, it lies there. So have differentiated product 3 times. We have that degree. So this is the result, and again, going back to ideals, it allows you to take an ideal, express it as a product, and work with factors separately.
So could you explain just intuitively why there is a non-symmetry in dealing with this H here? You said H1 plus 1.
Yes.
What is the main reason?
The reason is that actually this thing can be written as maximum of all expressions of this kind. That here you take hi, and here the rest. So I just said that I'm ordering h's. This is just shortening of notation. So this actually is symmetric thing.
Were there any prior results about this, and if yes, then how much better this is?
Oh, sure, yes. Okay. This thing is related to old problem differential algebra, which asked almost the same thing, but about membership not in some finitely many times prolonged ideal, but in the whole differential ideal. So it started from works of Gleb in 1942, where he proved some facts about which should be. Okay, he proved more general things. He found some degree here, such that this polynomial lies in the differential ideal. So you add infinitely many prolongations. And it turns out that in general, the degree obtained by Levy is lower, but the number of prolongations he really takes is bigger. So the result in pure differential algebra, it takes more prolongations here. So we need to prolong ideal more times, and that's the cost you can lower your degree.
And for the computation purposes, you perhaps want
for
to
the
lower the
computation purposes, you prefer not to prolong that much because this increases number of variables. So in computational setting, you in general prefer to deal with such truncated ideals, not with a very, very long prolongation. So,
because the degree bounds for, say, Grosvenor basis with the problem.
Yeah, they grow fast with variables. That's all. Thank you. Attention and questions.
Well, if we have time, maybe we go back to the lemma. I mean, I don't want to look at the general one. It's too complicated.
What?
Just the lemma.
Just lemma, okay.
Yeah, just the lemma. I just want to understand the notation better again. So, when you write I, an ideal, and then write the exponent, in braces, what do you mean by that?
I mean the ideal generated by all derivatives of all elements of I up to order h1. So not exactly, but
not
up to.
Up to. Not differentiating each time of the
Okay,
derivatives.
differentiation h time, differentiation h1, h minus 1 times, h minus 2 times, h minus 3 times, and
So up to.
Do you have this definition on the previous slide?
Could you write out that definition precisely for me, please? Because there are many ways to look at prolonged periods.
It's right there.
this.
Okay.
I less than equal to h.
Yeah, so you include many derivatives of lower order.
So it's all elements bounded by order.
Right.
Okay.
It's a traditional way of looking at this, transcendence degrees.
Maybe one suggestion is that the parenthesis notation is used in different ways. Why don't you put less than equal to h? That will help.
Yeah.
Definitely. Yeah.
Just put a less than.
Yeah, but okay, I mean,
And yes.
I'm not the person who invented this notation.
No, no,
so-
it's more the emphasis at the top.
Yeah, okay.
Kill
For the
all
purpose-
this ambiguity right away.
Yeah, okay, sure. Thank you.
And now the back to the
Lemma?
Equal h if you really want exactly h.
so lemma. So the notation x1, which is not an ideal
Mm-hmm.
to this exponent.
Yeah,
What does that mean?
This is exactly one differential polynomial x1 differentiated h1 times.
Okay.
So that their product there is just multiplying polynomial.
Yes, here's
There's the
polynomial.
multiplying ideal.
It's a monomial. This is a monomial, right?
Yeah, this is monomial.
Now, so suppose I again give you a witness for the lower one,
Mm-hmm.
and now from the I1 up to IN, I give you, let's say, an F1 in I1, which is, let's say, order less than H1.
Mm-hmm.
And the same thing for the other.
Yeah.
Just one of them is good now. In fact, I might as well take n equals 1,
Mm-hmm.
maybe. So then, so n equals 1, the bottom thing is true for t equals 1, is that correct?
Bottom is true for when n equals 1.
Yeah.
Yeah.
Yeah, it would be true for d equals 1. So that would be also true, yeah, for n equals 1, no problem, I guess. No,
So I have a question
No.
that it's
no.
probably something I
Oh,
missed.
okay, okay. Yeah.
What's the relation between
Okay.
the H and the HIs?
It is a sum.
It's the sum,
Sum.
I'm thinking.
So now right there,
Okay.
bottom line again.
Mhm.
So you have
So
to
that's
now.
how you deal with the case where the order is less than H1. Because the A, you apply it presumably with a smaller value of H1 prime, that's where your order is H1 prime for the choice that Bill is making. You have it's true there, so you can show it's true where you do the sum of the HI primes in the I1 up to IN, and that's less than the sum of the original HIs. So it's contained in that.
Yes, we have containment within this of this idea.
So presumably that's the way you do
So
it.
now I don't understand.
No,
Now I don't understand the top line now. So the elements I pick in I1 upper H1.
Maybe you should read the paper.
No, just this is one. So when I take something in I1 up to H1 braces, that element, let's say call it F1, that F1 is by definition in I1, is that correct?
if f1 lies in this ideal,
Yeah. It is in I1 because that's your definition.
No,
It's
it's not.
all the elements that is in
No, it's
I1,
not.
which is all bounded by H1.
No.
no, inclusion no. If something lies in prolonged ideal, it doesn't mean that it lies in initial ideal.
Whoa.
I
You
want
didn't
it-
say
I
for
want-
long. I just asked you for the definition of I1 upper H1, and you said it was all the elements in I1 whose order is bounded by H1.
No,
Generated by.
So you take all the elements in I1, and then you differentiate them
Generate all elements of a
up to
form
H1 times.
where A lies in ideal
It's
and
the,
I is some order.
it's the ideal, it's not necessarily the differential ideal.
Yeah, I1's not necessarily a differential ideal.
Yeah, because for differential ideals,
I will have to understand this thing notation one more time. I to H1 we denote the ideal generated by all the elements of the form A upper I. Now what's A upper I is the I to the root of A, right?
yes.
Yeah.
Where A is in I.
So for example,
And
if
is
I is the, let's take a differential ring, K of X.
I is a differential ring or not?
I is not a differential.
I is not differential ideal, it's just an
I is
ideal.
not a differential ideal. Oh, I is an ideal. Ah, okay.
It's just an ideal.
It could be a differential ideal.
Yeah, it could be, but again, it's a good situation.
Well,
In this situation, you
if
don't
a
need-
differential ideal, then it seems that the top
Yes, yes. If it's differential ideal, that's is meaningless because all
Yeah, it's
prolongations, you also need all
Oh,
prolongations.
okay. All right, I missed that. Sorry. So this is for ideal.
Yeah, but the differential ideal is in general not finite object.
So therefore, the element that you generate is no longer in I, generally
Yeah.
speaking, unless it's differential ideal. Okay. I always thought it was the differential ideal. Okay. Sorry, my mistake.
So in particular, this theorem would tell you something about divisors with normal crosses.
That's yeah, because locally, it's the same as
The atomic side,
hypersurfaces.
At least that's what it is. It looks
Yeah.
like that.
Yeah, sure. It's again just locally at this point. This is the same as just hyperplanes. So you get the structure of local rings by this thing.
No questions? Comments?
Let's thank the
Thank you.
speaker for coming up.